morning. So the first one is from Jeremy on 1Provably robust deep learning via adversarially trained.
Yeah. So I'm talking about some work that we did recently, which is sort of trying to optimize these recent techniques based on randomized smoothing to really kind of boost these numbers. This is joint work with a number of excellent collaborators. So here are their smiling faces. I guess this is Hadi Salman. He's a AI resident at MSR. There's Greg Yang, a researcher there. Han Zhang, who is an intern. Peng Chong, Ilya, and Seb. Okay, so try to work with them. Okay, so I guess there is some obligatory slide about neural networks, but Madri's in the room, so it's okay. It's okay. It's okay. I didn't change this at the last second. We're good. Okay, but there are these neural networks that they have adversarial examples. You can strip things and you can get these things to misclassify. And we've really talked about them a lot from an academic perspective, and it really is an interesting kind of philosophical, mathematical question why they exist. But I also do want to point out that there are very real-world applications and issues because we're using deep learning for increasingly important tasks. So for instance, here's a really interesting one from the Tencent Keen Security Lab. So this is they were using Tesla's self-driving system, and they were able to they put these dots on the road or something, and the Tesla autopilot thinks that there's a fake lane, and it tries to reverse into this lane in traffic. It's not great. So not only is it a very academically interesting issue, it does have very real security concerns in very real world settings. All right, so let's define the problem again. So we've seen a number of definitions already today, but I want to make a slightly different perspective on things, just because it'll be convenient for me in the future. So right now I'm just going to give you the standard definition. So what is it? So we have some classifier. It takes points in RD to some set of classes Y. And we have some perturbation set S, which for instance can be some LP ball or some set of small perturbations intuitively. Then the idea is we say F is robust to perturbations within this set at a point X if f of x is equal to f of x plus delta for all delta in this sense. Okay. For me, it would be slightly convenient to slightly generalize this, which is instead of taking classifiers, which you can think of mapping every point into a single class, I want to consider soft classifiers. Right, so a soft classifier, this is still pretty standard, but slightly different from what we've been doing previously. It takes every point in RD and assigns to it a probability for every class. And these probabilities sum to 1. So it takes it to the set of probability distributions over my classes Y. This is P of Y. Okay? But you can do the same thing. So I will typically denote soft classifiers with capital letters. And I'll say that a soft classifier is robust if sort of the most likely outcome of F, according to the probabilities that it assigns at X, is the same as the most likely outcome at X plus delta. Okay, for any delta in my perturbation set. In this talk, I'll typically focus on this perturbation set being the L2 ball. I think, as with the previous speakers, I don't want to get into this very moral and philosophical issue of what the right perturbation sets are. I will just say that perhaps, it might not be sufficient to consider such LP balls. I think people are converging to this opinion, but at least it seems necessary that we should be resilient to these sorts of perturbations. Okay. But in this talk, I'll focus not only just on LP, but mostly on L2, although I'll talk a little bit about L infinity at some points. Okay. So as Zico discussed in his overview, there's sort of two broad approaches to making neural networks robust. There are these empirical defenses, which I would characterize as they work the best in practice, as in we don't know how to attack them very well. But typically they offer no provable guarantees. And I guess sort of the most famous and arguably the most interesting of them is adversarial training and the variants thereof that people have been proposing. And there's been a lot of work recently because there's been this sort of, cat and mouse game. I guess, as Zico put it, you put out some defense and then Nicholas Carlini breaks it a couple weeks later. So, except for some notable exception.
Only one cut.
Yeah. Don't want to get beat. There's of course this notable exception of adversarial training seems to have, at least for now, stood the test of time. Okay, but to break the cycle, we introduce these certified defenses, which I would characterize as they provably work. They give you some provable guarantees on your test points. But often they don't scale to large, actually real-world neural networks, or they get worse numbers. So there are these, for instance, exact methods based on mixed linear interpreter programming, or satisfiability modular theories, which are like very exact. They actually give you the exact guarantees, but these are like integer programs. They don't, this is like NP hard stuff. Intractable typically. Although there's some work to try to scale them up. And then Zico talked a bit about his convex relaxations, which is the part of the talk which wasn't his talk. And then there's also been this very recently interesting line of work on randomized smoothing, which is actually what I'm also going to focus on. Okay, in particular, in this talk, what we're going to be focusing on is, can we somehow try to combine these nice properties? In particular, we know that these empirical defenses work well in practice, and we know that these have proofs. Can we somehow boost the provable guarantees of these methods by somehow tacking on these empirical defenses? And the answer, I guess, seems like we can. Okay, and specifically, I will focus on these two things. We'll show how to use adversarial training, done in a very carefully chosen way, to somehow improve the performance of randomized smoothing fairly substantially. Okay. So here's a brief outline of the talk. So I guess this is somewhat unavoidable, but I'll have to do a little bit more background on adversarial training and randomized smoothing. Then I'll try to get into our results and tell you how we achieve the numbers that we report here with these ideas of just adversarial training for smooth classifiers. And there's some subtleties there that I want to really get through, which are kind of interesting. Okay, so background, adversarial training. Hopefully some of you are at least somewhat familiar with this at this point, but the idea is empirically, and there's some justification for this based on these Danskin's theorems kinds of things. Training on adversarial examples seems to make the network more robust, at least empirically, although typically this offers no provable guarantees. So the idea is this is a typical SGD style update. I have some model. I have f and a loss function L, and f is parameterized by parameters theta t. So to update my models, without robustness, I would just do the following SGD step. I would say theta t plus 1 is theta t minus some step size times the gradient of the loss at a randomly chosen training point, xt, yt. Okay, but this is not robust, and to make this robust, the idea of adversarial training is instead of training on xt, you train on x hat t, where x hat t is some adversarial perturbation of xt for the current model. Okay? And ideally, xt hat would be the following. It would be the argmax. It's sort of the worst perturbation in my allowed perturbation set. So again, I'm taking L2 here. And by worst, I mean it maximizes the loss of my current model. Okay? So then I take this x hat t and then I plug it in here. And the idea is, and this is a point which we should be robust at, but we currently are not. So by doing this procedure, we're sort of, telling the algorithm to actually be robust. And empirically, this seems to work pretty well. And again, variants of this and also techniques that are added on this seem to get the state of the art for these robust tests. Okay, but again, these also do not typically offer any real provable guarantees. Okay, and I guess there's I should say, I forgot. We actually can't do even this process. This argmax is highly non-concave. So in practice, what we do is we do a first order approximation to this, which is, or variance thereof. I'm sweeping a lot of things under the rug. But one commonly used thing is something called PGD, which is simply, I want to argmax the loss, so I just take steps, gradient steps, in the direction of the loss. And then to ensure I stay within my perturbation set, I project back every other step and just repeat this process. This is PGD, and again, there are other variants, but this is the heart of what we're doing. The idea is that this is a first order approximation of this ideal argmax. Okay, so adversarial training. Now let me talk about randomized smoothing again, which Zico already described, but I want to describe this in a slightly different way, although it's more or less the same operation. So given a soft classifier, so one of these things that assigns probabilities to every point in X, in RD, the associated smooth classifier, you can write it in a number of ways, but you can think of it just simply as a convolution of F with a Gaussian with parameter sigma squared identity, covariance sigma squared identity. Alternatively, it's simply the expectation of F under many draws from a Gaussian. Okay, so when F is actually a hard classifier, or rather, I guess technically like the one-hot encoding of a hard classifier. These two definitions, this definition here and the one that Zico gave coincide, but this is slightly more general. That will be useful for us. Okay, and this is sort of a similar cartoon to what Zico did. This is from Zico's paper. You take this, I guess in this case, is a hard classifier. So, blue is sort of the thing classified as one class, turquoise is another, purple, so on and so forth. And then I take a point x, and then the associated smooth classifier gives you a soft classifier, which just associates these probabilities. It's simply the probability that a Gaussian drawn from this point lands in each one of these regions. Okay, and well, I should have said, I guess, as Zico pointed out, this is like a pretty recent line of work. It's very interesting, especially in the perspective of randomized smoothing. So it started by Lecuyer et al. And there's work by Lee et al. And also Zico's paper. And sort of the interesting thing that he pointed out is that you have this certifiable L2 robustness if you use randomized smoothing. So this is the bound in his paper. The other papers, again, proved other bounds, but this is, I think, the tightest one, and provably so. I'm just more or less restating still what he said in a slightly, I guess, more general setting still. So this is a multi-class setting, but you can still think of it as binary. It's more or less the same thing. But if F is a soft classifier and X is a point in RD, what we do is we take the most likely class of the smooth classifier, A, and we call P of A the probability that the smooth classifier assigns to this class A, and B is the second most likely class. We call PB the probability that the smooth classifier assigns to PB, and then the theorem in their paper is that the smooth classifier is robust at X for any L2 perturbation of size this, which is more or less the same thing as he said. Okay, so essentially, if your smooth classifier is confident about the prediction, then you get some L2 robustness for some radius. Okay? And again, there's these caveats, which I'm going to try to go through kind of quickly. We can't actually evaluate these very efficiently, but these are nice, easy things to estimate with high probability. You can sample them to extremely high precision with Monte Carlo sampling, and we're pretty confident that these numbers are correct up to an error of something like 0.1%. Okay, and I think most of the papers use kind of this number. It's a very small number anyway, so we should be confident that up to this very small failure probability, all of the things that we're saying are correct. Okay, and again, this is not like failure probability of anything but the internal randomness of the algorithm, because it's of the sampling. Yes?
So is this the probability that you use when sampling for every data point?
Yes.
But that does not mean that there is nothing in the test set. You have to take a union bound over your
test. So you should take a union bound over the test set, but I would say at the most, we should increase our error probability or the fraction of things which, the fraction of points which we say are certifiable by something like this %, right? And also empirically, from a very mild perspective, we took this, the sampling to be really, really large, and we just observed no differences. So, and that consideration as well, it doesn't seem to make a difference. Yeah. Okay. So now let's talk about our ideas. And the idea is that, as Zico pointed out, I think in his talk, you can't just take a vanilla network and expect that when you smooth it, you get nice numbers for anything. Because in particular, you're still doing this Gaussian smoothing operation fundamentally, and you're trying to classify with this smooth classifier. So the smooth classifier needs to work well. You can get good clean accuracy, otherwise you just kind of can't expect to get anything. So somehow you need to train a network to exploit the fact that in the end what we care about is the underlying or the associated smooth classifier, not the actual base model. Okay? And in his paper, what they did was they showed that Gaussian data augmentation is already quite effective, at least empirically. But as I'll get to in a bit, somehow it seems morally not quite the right objective. That we actually want to optimize. It sort of does the right things. It encourages you to be good under Gaussian perturbations and this kind of stuff. But when you actually kind of get into the more concrete things of what's going on, I think you can maybe get a better objective in some sense. Okay, and by using this better objective, you can get much better numbers. And that's what pretty much this work does. We provide somewhat more sophisticated training techniques, which allow us to substantially boost the certifiable accuracy. Okay, so let me show you some of the numbers now. Here's some of the experimental results. So these are the numbers that were reported in Zico's paper, or at least there's like our recreation of them. So they're like vetted. These are good numbers, both on CFAR and ImageNet, and these are certifiable numbers. So every column is a different epsilon radius, and this is like the fraction of points which we can certify using randomized weighting. Now I should point out that I believe this is a bit of a hairy statement, so I'm going to don't take this as word of truth completely, but my understanding is that the best empirical accuracy for L2 perturbations on CFAR 10 is this work by Roney et al., which occurred in CVPR in 2019. There might be better attacks now, I'm not sure, but this is some reasonable benchmark. And essentially, at epsilon is equal to 0.5, they got empirical accuracy, so not provable, empirical accuracy, 67%. And at epsilon equals 1, they got roughly 40%. Okay? So you can see these numbers are like kind of close, but there's still some gap here. And these are also numbers for ImageNet as well. All right, so with our techniques, we were able to boost this on both ImageNet and CFAR. So just by using sort of our vanilla ideas, we can already improve things by up to something like 14% numbers on CFAR and something like 6 to 7% on ImageNet. And then very interestingly, if you combine these techniques with more sophisticated things like pre-training or semi-supervision that like Ludwig's been working on, you can actually boost these numbers even more, and actually fairly substantially as well. So here I believe the best numbers that we can get. And it's actually, I think these are quite remarkable. In particular, if you look at, for instance, epsilon is 0.5, you get 65%, and epsilon is equal to 1, we get like 39%. So we're off from like some reasonable, I think perhaps the state of the art. Again, this is a bit of a murky business. We're off from these like reasonable numbers by 2 or 3%. So, and I don't think we've ever been in a state where like the provable accuracies have been this close to these empirical bounds, which typically do much better. Okay. And I also, I mentioned I was mostly talking about L2, but I also wanted to mention L infinity. So here are some results from this semi-supervision paper, which I believe get the best state of the art for L infinity certifiable accuracy on CFAR 10. So there's sort of two baselines here typically. So here is what they're doing is they're taking L infinity accuracy at perturbation level epsilon is equal to 2 over 255. For the famous papers, I think they typically, like the original papers, they take like 8 over 255, but this is also a reasonable benchmark, especially for certified defenses. And what the numbers that they got were something like 63 or 4% certifiable accuracy at L infinity 2 over 255. Well, we do L2, but if you make your L2 ball big enough, it contains a corresponding L infinity ball. So if you just use the trivial embedding of L2 into L1, and just like see what numbers we get at that radii for L2. When you take the corresponding radius for L2 for L infinity corresponding to 2 over 255, we actually get a certifiable bound of 68.2%. So I believe also just using naive L2 techniques, we're able to improve upon the state of the art for L infinity, at least for small radii.
So this is the L2 ball that contains L infinity.
Yeah. So just certainly if you're robust to perturbations there, then you're also robust. It's kind of surprising that you get like any reasonable numbers here because there's like a huge root D distortion in theory, but these are the numbers. So it's kind of nice. I should say that this does not, as far as we can tell, give you state of the art for epsilon is like 8 over 255, which is like one of the other standard benchmarks. It does give you something like 25%-ish, I think. And I was quoted that like the state of the art certifiable is something like 35%. So we're like not great, not terrible. Okay. So how do we actually get these numbers? So how do we actually train for effective smoothing? How do we improve upon the training that was proposed in like these in Zico's paper, this Gaussian data augmentation? Well, we have sort of two key insights. First is that we should always be directly working with the smooth classifier. There's no reason in some sense, at least from a moral point of view, ignoring things like optimization, to not work directly with the smooth classifier. And it seems like Gaussian data augmentation is doing something like this, but it is not, and I'll explain in a second. And the second thing, which is not really a super novel idea, but once you get the idea that you should always be working with the smooth classifier, like just only ever with the smooth classifier, it makes sense that you should just try to encourage the smooth classifier to be as robust to perturbations as possible. Certainly if it is not robust, then you can't certify that it is not robust. So you should just try to do whatever training method that's going to make the smooth classifier as robust as possible. Okay, so this leads to the natural idea. Certainly we should just adversarially train the smooth classifier as well as we can. Okay, this is more or less what we do, and when you do this technique, then this is like how we get these nice numbers. Okay, so how do we work with the smooth classifier? How do we work? Okay. So a little bit of notation first. Let me let x1 through xn be the, x1, y1 through xn, yn be the training set, and let L be a loss function. Typically just think of cross entropy loss, for instance. Then what Gaussian data augmentation is doing, it is minimizing the following loss. Okay, it is minimizing the sum over my data points, or really you should think of the expectation over the training distribution, for this is a finite regime, of the following. The expected loss of my function at a Gaussian perturbation, because I'm training my model on Gaussian perturbations. I want my model to work well on points where I have Gaussian perturbation. So this is sort of intuitively what Gaussian data augmentation is doing. Okay. But that's not quite what we care about, because what we care about is simply the loss of the smooth classifier. So sort of the objective that we care about is the loss of g sub f of xi, which you can write out in this way. All right, so the sums don't really change anything, so let me just write the thing for a single, or actually let me not apparently. But yeah, let me just write these out more carefully. But you can see that there's a subtle distinction here, which is, I mean, it seems kind of silly, but this L, we pull it outside. Right, but this is a very, from a moral perspective, a big difference, because the former never talks about the smooth classifier. It's just telling the base classifier to somehow be robust to random Gaussian noise. But we don't, at some level, care about that. Right? It might be a good proxy for it, but what we really care about is that the smooth classifier itself trains well. And so this is what we should be doing. We should always be working directly with functions that have the loss of the expected perturbation. Okay. And this is super important for getting the numbers that we get. And this will also come up in one other place. Okay, so as long as we ensure that we do this, some of the natural, the other ideas just kind of follow fairly naturally. So, I want to not only train this, the smooth classifier, but I also want to make it robust. I want to adversarially train the smooth classifier. So how do I do this? Well, again, so this is the original adversarial training. For a base classifier, I find an adversarial perturbation of my function f. And this is my idealized kind of perturbation. Instead, what I should be doing is now I'm going to be doing an adversarial perturbation. So I'm going to be taking the loss of the smooth classifier here. And I'm going to be finding an adversarial perturbation of the smooth classifier. Okay, so this is what this is. So far, hopefully makes sense. And again, we can't do this exactly. We have to somehow approximate it using some first order objective. So we're going to do some sort of PGD kind of attack to do this. Although we also investigate the performance of another attack here, like this recent CVPR paper, this decoupled direction and norm. Again, it's some sort of descent method or ascent method, some sort of first order descent method, but the performance is similar. So I'll just focus mostly on PGD for the talk. Okay, but this is more or less what we want to do. And again, I want to emphasize this point, which is that this is the perturbation that we're trying to find. We're trying to find an idealized perturbation of the, we're trying to find a perturbation of the smooth classifier. So this is the loss of the smooth classifier when I write it out, when I expand out L of G sub f. And we call this a smooth adversarial objective. And importantly, this is not the objective, which looks very similar and which we got confused by at some point and we tried. Again, this thing where the expectation is on the outside. Okay, which from a number of optimization point of view, like from that perspective, this is like much more natural. But from the perspective of actually trying to find adversarial examples for the smooth classifier, this is definitely the thing to be doing. I'm just like, I feel like I'm saying this a lot, but to hammer this home, what this is saying is find me an adversarial example of the truest smooth classifier. Find me a point such that the Gaussian majority vote will be wrong at this point. And this is saying find me an adversarial example of f that is itself robust to Gaussian noise. So find me an adversarial example for the base classifier such that when I perturb it, it is robust. And this is, we don't care about this in the end. Like it might be a reasonable proxy at some level for this, but we don't care about it. We really want to directly optimize this, even though this like makes our optimization life a bit worse. Yeah.
So there is no direct formula you can write for the hard classifier on the left side.
No, it's a bit messy. Actually, so there's like things you can actually do, which like you can actually write down exact gradient forms for this. I'm not going to talk about this too much in the talk, but for whatever reason they don't work very well, and so much more naive estimators work better. Yeah.
So for each step of PGD for finding an adversarial example, do you need to evaluate the smooth classifier, right?
Yes.
So you do Monte Carlo sampling at each
Yes.
iteration?
Yes. So this is actually one of the things that is a limitation of the method, which is that adversarial training is already really slow. We can only do like 10 iterations maybe, and that's already going to blow train time by a factor of 10. And then when you do, this is going to make it also bad. So there's like.
How many samples typically do you need in practice?
So I'll show you some of the hyperparameters in a bit, but I think we try at most something like a relatively small constant, like 10 or so. And that's like just a limitation. Although I should say that we only use like 10 samples for train time, but when we evaluate, we still use like 1,000, 10,000 or whatever. So this is going to give you some weird heuristic for training, but in the end it does give you better certifiable numbers with high confidence.
You're talking about the Gaussian noise or smoothing as being completely symmetrical. And one of the interesting points from Alex's talks was that we should not be doing it symmetrically because there are the directions of more and you have to be kind of suitable to the shape of the data.
So from a heuristic perspective, definitely it seems reasonable to try to do this, but if you want to get like certifiable numbers at the end, as far as we know, unless you have some prior about like the shape of the distribution, the best we can do is just take, at least for L2, just take the standard Gaussian and use like the Neyman Pearson style results on that. It is reasonable actually, and this is something we were interested in trying out. It's like during optimization, instead of using like a standard normal Gaussian, try to adapt that to the shape of the distribution somehow. But
even just using unlabeled data.
Yeah, for instance, but we're not sure how to do that. In particular, it's like even if you're robust to perturbations in a different Gaussian, it's not clear then you'll certify well with a nice spherical Gaussian because these are also kind of already different objectives. But it's still interesting. Yeah, we're not entirely sure how to optimize this. This is just sort of a first attempt. Yeah.
So it looks like there's kind of a free temperature parameter you might want to have there.
Ah, yes, good. Yeah, so this is a good observation, which is that there's another perspective on this, which is that somehow this is sort of approximating some sort of like softmax, or like getting rid of some sort of softmax. And it is actually very interesting to try to vary this temperature parameter is associated with a softmax, although in practice for whatever reason, when you do it on like TensorFlow, it's always set to 1. But you can try like it is interesting to like try, for instance, like the low, whichever one corresponds to softmax approaching to max, these kinds of things. We wanted to try this at some point. I forget actually if we did. Yeah, it's a
because it's just a surrogate for like the
exactly.
classifier that takes the actual mass.
Exactly. Yeah, exactly. If you take sort of like a free temperature parameter that's going to this, you actually take the like something that's going to the hard classifier, and that's like at the very end what you like cared about originally.
But you mentioned that it doesn't work, right? The hard classifier version of the left doesn't work as well.
Yes, at least empirically it does not seem to work as well, at least in our experiments.
You don't want to be in low temperature.
Well, I mean, maybe you can do something. We don't claim that we've done everything, exhaustive. But I think it's interesting to try the things, because in the end, it is very natural to try to do the like the actual hard classifier here. Particularly, you can even take gradients of it, which is nice. But yeah, to drive this point home that like, this objective yields stronger attacks than this objective, this is just a plot. So sort of the black line is the performance of this attack. So lower accuracy means a stronger attack. And as you can kind of see, I mean, it's kind of squished down, unfortunately, but as you do the smooth adversarial objective with enough samples, like something like even 8 or so, you're going to like beat this attack, especially like in a small L2 radius regime. And typically, at least in one of the, we believe about adversarial training is that the stronger the attack, the more robust the resulting model, which makes sense. Your training gets harder things. And so this difference actually seems to result in like a big difference in numbers. Yeah.
So how tight is the adversarial attack with the certified?
Yeah, I'll show that curve in a second. It's like sort of tight at points, but not always tight for sure. Yeah.
Why are they different for m equals 1? Why aren't they the same? When you have one
That is
sample.
a good question, actually.
Hyperparameters?
I'm not sure. Let me get back to you on that. Yeah, very interesting. Is there another question somewhere? Or? Okay. All right. So yeah, we want to always again work with this smooth adversarial objective. So then the main question for all these things is how do we evaluate gradients? Okay. So we need to evaluate gradients of the smooth classifier. And again, we're going to focus on the cross entropy loss. When you do so, we need to both be able to take gradients with respect to x and theta. So we need to take gradients with respect to x to actually find adversarial perturbations, and gradients with respect to theta to actually do the update steps. But the problems for the two are more or less the same. So I'm just going to focus on taking the gradient with respect to x. And you can write it out, at least in the infinite sample regime where I take many samples of delta, as this kind of formula. And there's actually a number of nice things you can do with this formula that we don't end up using. Like, this is what gradient of a log is. You can just do that. And this is just the gradient of f convolve a Gaussian. So you can take the gradient of f convolve a Gaussian. In fact, even in a gradient-free way in terms of f, right? The derivative of f convolve anything is it's either the derivative of f convolve that or f convolve the gradient of that. And the gradient of a Gaussian is like very nice. It's like this thing called Stein's lemma. It's a very classical statistical effect. So you can do like nice closed form formulas for this that you can then approximate via Monte Carlo sampling and get like nice unbiased looking estimators for it. But we tried these things, and I can show you the numbers, but they don't work. We conjecture this is because the resulting estimators that you get have extremely high variance, and we are in this extremely limited regime where we can only take a very small number of samples. And that's probably why they don't work, but we're not sure.
I see, because your sigma is high, basically, high variance.
The sigma is small.
The sigma squared?
Yeah, sigma's. The issue is that the dimension is going to be large, right? The dimension is d. So somehow.
Oh yes, yes.
Yeah. So when you take the sort of the Stein's lemma based estimator, this corresponds to like sampling a bunch of directions and kind of downweighting the ones in which they're bad, based on f. And somehow this seems to have too much variance to actually be a reliable estimator unless you take too many samples. So despite the fact that there's like cool things that we tried, the following very naive estimator, which doesn't have any frankly nice properties as far as I can tell, worked the best empirically, which is simply I approximate this inner expectation with a sum of regressions. Yeah. It has one redeeming factor. It is in fact asymptotically optimal under some mild assumptions. Like it will converge the true gradient, but that's pretty much it. It is not unbiased, at least from a theoretical perspective. And again, there are these much more sophisticated things that we could have tried for the gradient that just don't work in practice. Okay, but that's pretty much it. So the full algorithm essentially goes like this. For x, y in the data set, what we do is we find an adversarial example for the smooth objective. So we take x hat to be x plus noise, and then we iterate this process with projections. So that's the type of projections here. And then we just train on x hat with respect to these this adversarial perturbation. And we train not f, but g, the smooth classifier. And again, for whatever reason, the best thing to do is to take the plug-in estimator. At least that's what we thought. Yeah.
But rather than thinking as to whether you have an estimator and whether that estimator is accurate, why not just think that this is a stochastic gradient? And therefore maybe there is a difference in training due to gradient versus stochastic gradient.
But like, what is this a stochastic gradient of even? It's not.
Of the expectation.
That's not true.
The gradient of the expectation is
No, but it's a gradient of a log of an expectation.
I don't know.
So it doesn't even have this nice. It's a gradient of something else. In fact, you can say something. It's not. Okay, it's not like I'm like maybe saying it's too bad. For instance, in some sense, if I normalize away the norm, you can couple this with the an unbiased estimate of the direction, because the log pulls away, and then you do get something which is linear on top. But the directions that you get are completely arbitrary, and you get some kind of, at least mathematically, I think I can say, yeah.
Is it a fresh stamp, a fresh batch at every PGD step? Or is it the same, like I goes from 1 to n?
Good. I forget exactly. I believe it is the same. But it didn't make a huge difference.
And did you try to estimate the variance?
That's a good question. I don't think we tried to estimate the variance. Yeah.
So just to make sure, at this point now, your theorem technically no longer applies, right? Like now it's a method inspired by.
Well, so the training never had a theorem, but in the end we're going to get some classifier.
But what are the guarantees that it is actually robust?
Well, then what you can do, you evaluate, you evaluate the smooth classifier. You get these at a point x, and then you evaluate the, PA and PB, and you see how big what the gap is, and then that gives you some radius at which you can certify at that point.
So as in you would run through every example in order to.
So this is on training,
right?
and then after we get some model, what we're going to do is we're going to go to the test set,
Okay.
and then perform this procedure and see what fraction we can certify. And that is like our estimate of like what fraction of the points from the true distribution we can certify. So from that point of view, it's still legit. Yeah.
Or just to rephrase, so you can still apply Zico's theorem. It's just a method to boost the P.
Right, exactly. Just the method to try to get something that makes Zico's theorem stronger. Yeah, in the end. Okay. We have a number of hyperparameters which I'm not sure I want to get into, but this is somebody asked this at some point. For instance, the number of noise samples we used during training was very small. It was like 8 or so. This is a clear limitation of our method, but it seemed like it's very like doing this on like CFAR and ImageNet already took like a lot of MSR GPUs, and we have like a fair number of GPUs, and like people got angry at us. So it would be very interesting to like do more, but it's already pretty hard to like do this kind of stuff. Right. So here are some plots corresponding to some of the numbers. So the left plot is sort of the upper envelope plot. So the x-axis is the L2 radius of the oh yeah.
Sorry. M train was 1248. That was the number of samples in this.
And yeah, when you use to estimate the Gaussian noise.
Just 8?
Yeah. Because it just, the more Gaussian noise that you use, sort of the longer it takes to train, like by a linear factor, and like adversarial training already takes 3 weeks. So.
But just to be clear, earlier we had this question about whether those 8 are the same across iterations. They have to be different then.
Well, so it's like definitely during like different. If I like choose a new sample X, they'll be different. Yeah. But sometimes amongst the 10 steps of PGD we can reuse those because these are all tiny numbers. Yeah. Okay. So left plot is the upper envelope. So there's like for every epsilon, what is the model that gets the best certifiable or empirical accuracy? So red line is the numbers from the CMU paper. So the solid lines are always the certifiable accuracies. And you can see, and the dotted lines are the empirical accuracies that we got by trying to get as our strongest attacks against them. And so, we do substantially better, I would say. In particular, it's very interesting. We actually do better than the empirical performance of the attack certifiably. And this also answers some other question, I think, which is that there's still some gap between the upper envelopes, between the certifiable and empirical accuracies that we get, although it is somewhat smaller, which is nice. Okay, the middle plot is a similar upper envelope plot. So what we do is we take the best model for a fixed sigma. So sigma was the hyperparameter which control like the Gaussian variance that we had. And for every sigma and for every epsilon, we found the best model. Applied our certifiable empirical accuracies compared to the CMU paper. And again, we had improvement. And just to make sure that we're not like doing this just because we're doing like a huge sweep over hyperparameters, because we do a much more dramatic sweep over hyperparameters than the CMU paper does. We also just tried some, like we found some representative models, like more or less randomly selected, where like Hadi went into some files and there's like a huge file of files, clicked on one and got these numbers. And again, even for fixed models, so each one of these lines now represents a single fixed model, we still do better. Okay, and also you have results for ImageNet which are similar. And these jumps are artifacts of the fact that we couldn't run as many things on ImageNet. Like these are literally the fact that we don't things. So those aren't real, but that's just because ImageNet takes forever to run. But okay. So as I mentioned before, we can also boost these methods even further by kind of combining this technique with some other recent ideas. So there's this paper by Hendricks et al. Which showed that pre-training on some sort of downscaled ImageNet and then like fine-tuning this model on CFAR10 improves the robust accuracy on CFAR10. So if you do the same thing, so you pre-train a smooth classifier on ImageNet that's robust using this technique, and then like fine-tune it empirically, you can try that, and it turns out it boosts the accuracy a lot. Similarly, there's a result by,
Name you can pronounce.
Carmen et al. Which showed that you can use like unlabeled data to improve empirical robust accuracy on CFAR10. So we kind of use the same technique, semi-supervision, but again for smooth models. And again, by combining our techniques with them, we obtain like even higher certifiable accuracies as we showed in the original table. I'll show it again in a second.
We also do randomized smoothing in our paper.
Yeah, but I guess somehow, yeah, that's true. Yeah, you guys do. Yeah. There's a very interesting point I wanted to make. I don't really get why this is happening. There's some weird things with the numbers, or coincidences or something. I'm not sure what it is. Essentially, both pre-training and supervision, kind of, or semi-supervision, seem to help our numbers dramatically. Like you can see, you can get like 82. These are like much better than before, and they're very similar actually, right? Like somehow they're like off by 2%, and then combining them does barely anything, and oftentimes doesn't even help. I don't really understand why that's happening, but it's interesting. Yeah,
so if you assume that the smooth base model helps, why didn't you just do bound propagation and make it like smoother, like from your base model?
Sorry, what kind of bound propagation?
So like for example, like the ones like Zico or like the previous work on like the.
I mean, it's a reasonable idea. I'm not sure it quite makes sense because you're like combining L2 and L infinity kinds of things.
Right.
But we didn't try it for sure. It's also like, this is already like took forever to run on.
It's quite possible that I haven't been careful choosing M, right? Seems very critical.
Actually, we
combine these methods. How would you may sacrifice? Just a number.
So we performed some ablation studies, and some of the plots are actually somewhere I can probably like maybe flash them. But choosing M, at least like a slightly larger constant, didn't seem to change things too much. Very interesting. Not sure why. There's a lot of unexplained phenomena here. I mean, we get like these numbers, which, to my understanding, are like state of the art and very nice. But there's a lot of stuff that we don't understand about like why these are happening, which are very interesting questions. Okay, so that's pretty much all I want to say. In summary. I hope that you take away from this talk as well as Zico's talk that randomized smoothing is an extremely powerful technique for training these provably robust models. And by combining adversarial training with this randomized smoothing, you can substantially boost the provable accuracy that you can get. But there's still a lot to be explored, so there's a number of open questions. The first thing is that while it seems like these things help a lot for the small epsilon regime, when your epsilon is like relatively large, like epsilon is equal to 4, so the boost is much smaller. And also, very interestingly, pre-training and semi-supervision just don't help at all there. Like, at all. It's very weird. It helps so much when epsilon is relatively small, but just nothing when epsilon is large. And again, I think a question that a lot of people are interested in is like, can you do some other norms like L infinity with some other smoothing mechanism? Who knows if it's possible or not? We'll see. And of course, a big question for a lot of people is like, can we go beyond LP? Like, can we do smoothing for some non-Euclidean norm, like I don't know, Earth mover distance or these sparsity inducing norms and this kind of stuff. Okay, that's pretty much it. I'm told that if you scan these, you will get links to the papers, but I don't have a QR scanner, so. But also, if you can just probably search on the internet, and yeah, you'll find it too.
We have time for 1 or 2 questions while the next speaker comes up.
Did you take a look on like the certified robust accuracy, the gap between train and test set? And is it big or small?
I don't think we tried that. Yeah. That's an interesting one.
Any other questions? Thanks again. The next stop will be given by Venue on interpreting neural network.
Okay. Thank you very much, the organizers, for having me. So my group has been doing a lot of empirical work and especially try to use deep learning for science. And it's a great